Hello everyone, I'll be talking about the preparation of silicon dioxide and how it's reduced to elemental silicon for our solar cells. Silicon dioxide is prepared industrially using the sol-gel method because it allows chemists to control the purity and surface characteristics of the final silica product. In the sol-gel synthesis, tetraethyl orthosilicate is commonly used as a silicon precursor. The reaction typically occurs in the solvent mixture of ethanol and deionized water, with either hydrochloric acid or ammonium hydroxide as a catalyst to control pH. The hydrolysis step occurs at room temperature around 25 to 40 degrees Celsius, where water molecules attack the bonds of tetraethyl orthosilicate to form silanol groves as shown in this equation. Following hydrolysis, condensation occurs, where silanol groups react and release water or ethanol, forming strong silicon-oxygen-silicon bonds, building a 3D silica network, forming a semi-solid gel. Once the gel is formed, it is aged for 24 to 72 hours at room temperature to allow condensation to be completed, and after it's dried at 80 to 120 degrees Celsius to remove trapped solvents and volatile byproducts. It is then calcined in air at 450 to 600 degrees Celsius for 2 to 4 hours to burn off organic residue, resulting in a silica powder of over 90% purity. For industrial scale silicon production, to raise the purity level, silica undergoes acid leaching using 5 to 10% hydrochloric acid to remove impurities like iron oxides, then thermal treatment at 800 to 1000 degrees Celsius for 2 to 6 hours to remove volatile impurities. The purified material is then crushed and sieved into fine grains of a finer silica powder. It is then converted into elemental silicon by a carbothermal reduction process, which is carried out in a submerged electric arc furnace operating between 1900 to 2000 degrees Celsius. In this step, the silica powder is mixed with a carbon source such as coke or graphite in a 1 to 2 molar ratio. When an electric arc furnace passes through the mixture, the silicon-oxygen bonds are broken, and carbon reduces the silica to elemental silicon, releasing carbon monoxide gas as shown in this equation. The silicon formed at this temperature collects as molten droplets at the bottom of the furnace and is called metallurgical grade silicon and has a purity level of 98% silicon with remaining impurities such as iron and trace carbon. The reaction is endothermic, requiring roughly 35 to 40 megawatt hours of electrical energy per ton of silicon produced, and takes several hours of heating to complete. To achieve extreme purity needed for semiconductor and photovoltaic applications, this grade of silicon undergoes chemical refining steps. A common industrial route is the Siemens process, which converts crude silicon to volatile trichlorosilane gas by reacting it with hydrogen chloride at 300 degrees Celsius, as shown in this equation. The trichlorosilane is then purified by fractional distillation, which removes metallic and boron impurities. After purification, the gas is decomposed on heated silicon rods at 1100 degrees Celsius, depositing pure elemental silicon with a purity level of 99.99%, known as electronic grade silicon. It is then melted at 1420 degrees Celsius and solidified to form large ingots of single crystal silicon. The ingots are then sliced into thin wafers, usually 150 to 200 nanometers thick, then cleaned and chemically etched to remove surface damage and contamination. Each wafer is doped to create a p-n junction by introducing a small amount of phosphorus to the surface of the silicon wafer to create an n-type layer, while the bulk remains p-type. The resulting interface between p-type and n-type regions allow charge separation when light is absorbed. When sunlight hits the silicon wafer, photons excite electrons in a crystal lattice, freeing them from their atoms, and then the electric field at the p-n junction drives these electrons towards the n-type layer, and the corresponding holes towards the p-type layer. The solar cells are then coated with an anti-reflective layer, usually made of silicon nitride, to reduce light loss and encapsulated between glass sheets to protect them from moisture and oxidation. Multiple cells are wired together to form a solar module, which converts sunlight into usable electricity with typical efficiencies of 18 to 22% for crystalline silicon cells. And these are my references in this slide. Thank you.